Before we get into the new functions that we're learning and domain and range, you have learned about two types of functions already. You've learned about lines, that y equals mx plus b, and then you learned about quadratics last year in grade 10. You learned about x squared, right? That U shape. And so you're going to learn three new functions today.
Good morning, Lisa and staff. Of course, it's quite stormy out there, so I hope everybody is here safe and sound. Students are arriving. Please wait until 9:15. So we're just going to allow a little extra time due to the weather. So please wait till 9:15 before we start marking anybody late and sending them down for late slips. 9:15, please.
Coolio. So, as I was saying, you're going to learn three new functions today, and you're going to not only learn how to graph them normally, but you're also going to learn how to transform them in this unit. So, like, can you shift it left or right, up and down? Can you do the vertical stretches like you learned with the parabola, where you make it like thinner or wider? Reflections, all those kinds of things are coming back. So that's what we're going to be able to do. But first, when we talk about all these types of functions, we talk about things called like the parent function and the families of functions. So for example, with a family, right, that is a collection of functions that have like the same characteristic. So for example, like a parabola, we could say f of x equals x squared, right? We could also say like that is our original, if I did like a little sketch here. Ooh, there we go. It always changes on me. So that's our original. And then we could have other family members where maybe we've stretched them. So this one's like a little wider. Ooh, not crooked like that. A little wider. They could be a little thinner. Oh my God, I hate the little correction tool. There we go. All right, little rough sketch, but just shows that they come from the same family. They look a little different, right? There's been some transformations applied to them, but they all come from x squared, and they have the same common characteristic of, like, for example, their origin is at 0, 0. That's a common characteristic. So they all belong to the same family. When we talk about the parent function, which is what you're going to hear a lot, that is like the base function. That's like the original that you started with before you've performed any transformations to it. It's like saying like y equals x. That's the original line. It hasn't been shifted up or down. It's got just a slope of 1. It's plain, right? Same thing with x squared. It's just the regular parabola. It hasn't been shifted up and down, left or right, hasn't been stretched or compressed. It's the original. So that would be, like we said, f of x equals x, or f of x equals x squared. Those are parent functions. Okay? And you can think about their like transformed functions being like little babies that come from them, right? When we talk about domain and range, we said it yesterday because I think some of the homework questions ask you about domain and range, and then you were kind of like, ooh, what's that? Domain is like the set of all values that your function is allowed to have or allowed to touch or can take on, essentially. Whereas range is the opposite. It's all the y values. So like how far, how tall can your function be? And we use specific notation when talking about domain and range. So even just on like this little right side, I wanted to go through some of the set notation characteristics. Notation, where you learn these in elementary school, but a lot of people still forget them. So for example, if you have something that looks like this is just saying that x is greater than this number. Right, greater than n. Ooh, it's cut off there. Perfect. Right, so it's like the alligator. I don't know if you ever saw that hack of like the alligator eats the bigger number if you draw teeth on it versus like it's a mouse. If it's like you draw the little nose and the whiskers, it sniffs the smaller number. So that's like one way to remember it. If I do the flip, this is just going to be x is less than n. If I add a line underneath, so for example, if I did like x is greater than or equal to, that's what the line is saying, that it can be that value and everything above it. So x is greater than or equal to. Which we're gonna see those differences play out. Because for example, if I say a function has to be greater than 1, it means it can't be 1. It could be like 1.1 or 1.001, but it just can't be 1. Versus if I say it's greater than or equal to 1, then I can include 1. It can be 1 and everything above it. If I've got some sandwiching going on, so for example, if I've got like this, where, ooh, there we go, n1 I'll say for one number, and n2 for a number. So x is kind of sandwiched in. That just means x is greater than the first number, which we usually kind of do it from like least to greatest, or most negative to most positive. It's greater than n1, but less than n2. So it's in between those values. And then the same thing as if I do, for example, the lines underneath. That's just me now including those boundary points, or like those endpoints in your domain and range. So this would be x is greater than or equal to n1, but less than or equal to n2. Less than or equal to n2. So the lines just indicate whether or not you're including that boundary point. So, okay, now that we've got all of that notation out of the way, and I promise in grade 12, the notation becomes nicer. Set notation's kind of old and outdated, so you learn like a cleaner, more simpler form of describing domain and range if you take advanced functions in grade 12. But for example, if you've got a set of ordered pairs or coordinate points, ordered pairs, then you're going to describe your domain and range as like, okay, my domain is going to be x equals, and then you're going to do these fancy brackets, and you're going to list each number. So you're going to say, for example, like n1, n2, or I should say x. I'll say x, x1, x2, x3, x4, and you're going to list all of the x values that are in it. So for example, if you're given like a set of 5 coordinate points, you're going to list all 5 x values in ascending order. Same thing with range. If I give you just like 5 coordinate points, you're going to list all 5 y coordinates. 2, y3, y4. So I think one of your questions had like, instead of a line connecting all of the points, it was just like random dots on the grid. That's when you would use this type of domain and range, because you're saying my domain is specifically going to be 1, 2, and 3. I can't say it's between 1 and 3, because then that would apply like, or imply that I'm saying like it could be like 2.5 or 3.3, and I could get into the decimals where it's like we can't do that. I'm just saying it's either exactly 1, exactly 2, and exactly 3. Nothing in between, right? Versus if you've got a function or a graph, right, where the line is connecting all of these dots, then you can use those boundary points. So we would say domain. This is where we use the fancy XER, such that, and then this is where you would state whatever restrictions you have, where you say x has to be between certain values, x has to be greater than or less than something. That would go in that part where you're saying like x is a real number, but, and then you would describe the restriction. Same thing with range. YER, which just means y is a real number, not an imaginary number. And then you state your restriction. So again, is there a cap on like how high this function can go? Or what is the absolute minimum of this function? That's where you would state that stuff. And we're gonna practice doing it. Is this slowly starting to come back to you from grade 10, seeing this notation? Yes? Okay. Arturo, did anyone come in late? I don't think anyone joined us after, so I can submit attendance. Okay, this is fine. Okay, am I good to flip? Yes? Oh, perfect. Chloe. Yeah, I'm changing you right now. Perfect, you're good. Okay. It's okay, I'm good to flip? Okay. when we go to practice this is exactly what we're doing this here, where first I'm giving you ordered points and I'm saying, describe the domain and range of these points, right, of this relation. So like we said, for domain, I'm gonna look at what are all my x values. So I'm just gonna take a highlighter and be like, okay, 3, I've got 5, -2, 5, and 6. So those are all of my x values. So I know I'm just gonna list them. But now I'm just gonna do it in like ascending order. So I'm picking the most negative and then I'm just gonna increase like as I go across like a number line almost. So it looks like my lowest value here is -3. Then I've got, which I'll check off as I do it, -2. Then my next lowest, it looks like I've got 5 repeating twice. And then 6. Is this function, or is this relation a function, or is it just a relation? Can we tell? It's a relation. Why is it a relation? The 5 repeats. See, it comes back, right? So, okay, we're good with this. And then I'm gonna just do the same thing for the y's. So my range is gonna be y equals, and I'm gonna take another color and just be like, okay, in pink, these are all of my y values that I have to account for. And I'm gonna go lowest to highest. So what even is my lowest one here out of all of them? Yeah, -8, then what? -6, yeah. What's next? 3, 4, and 7. Perfect, right? All done. And that's it. So that's why I use the coloring system, just to like know that I'm on track, I'm not leaving any out. And if it helps to sort them, you can do that, but it's just listing. Okay, what about this one? What's my domain gonna be? I have to list points, and I'm gonna say x equals. Okay, what's my lowest x here? Which I'll do in yellow, I'll highlight them for you. What's my lowest one? -1, yeah. Then, and it looks like it's already in order. 2 and 3 and 4. Perfect. Is this a relation or a function? This is a function. There's no repeating x values unlike this one that we had up here. So it is a function. And I'm gonna do the same thing for range. So if I take my pinks and I go through and just account for everything, it also looks like it's already in order. I don't have to do any jumbling up or mixing. It already looks like it goes from -2, 1, 3, 5, and 6. Not too bad, right? Is this okay so far? Cool. When you've got a graph, sometimes you're gonna see, especially if it's like restricted to a certain domain, because some functions will just go on like forever and ever and ever. And so that is denoted by some of these symbols. So for example, if you see an endpoint and it's an open circle, it means that endpoint is not included. All right, so we are not including that in the domain. So that's when you would use like these symbols, right? Where it's like, okay, it's has to be greater than or less than this value, but it's not this value. We're not including it. Versus the closed circle, that just means the endpoint is included. Is included. And that's when you would use the set notation where you've got like the line underneath where you're saying it's gonna be greater than or equal to this, or less than or equal to this. So it's touching it, it's including it. And then if you just see arrows, you don't see any circles, open or closed, it just means that the function continues forever. So there's no restriction. It continues forever. No restrictions. Meaning like it's not cut off anywhere. So we're gonna practice this. So even with my first one here it looks like I've got 2 closed circles. So those both endpoints are included. So if I wanna think about domain, I'm just gonna look at what are my x values allowed to be. So even if you wanna draw colors and almost like box it, it looks like I go from here to here. And I'm stuck in that domain where it's like all my x values will fall between those 2 values. So I'm gonna just describe that as XER such that, and then this is where I have to say, it can only be between -2 and 2. So I'm gonna use that sandwich notation that we said, where it's gotta be less than or equal to -2, or sorry, greater than or equal to -2, but less than or equal to +2. Right? It can be everything in between that. It could be -1, it could be 0.5, it could be any of those decimals, it falls in between there. And then I'm doing the same thing with range, where if I take maybe a darker color, I'm gonna do my like most bottom Y value, which it looks like it's there. And then this is my highest Y value. So I would say, okay, that's my range, where Y is an element of the reals, such that though, and again, I'm doing the sandwich thing where I'm saying Y has to be greater than or equal to -3, or less than or equal to 1. If it helps to put your variable in the middle first and then kind of build the notation around it, you could also do it that way, right? But was how I found those numbers or decided what method to use or like how to write the domain and range, was that okay? That was okay? Okay, then you tell me, what about this one? It looks like I've got a closed circle and then I've got an open circle. So that's gonna impact our domain, right? So what X values am I between right now? What's my lowest X value? Yeah, -4. And then what about my highest one? Where does it go to, it looks like? Right here, about 4, right? The open circle just means that it's not equal to 4. So it's like touching 3.9999, but it's not touching 4. That's all it means, so it's close. So, okay, we know that if I had to use the sandwich method, right, for XER, that I'm saying, okay, it can be -4, so I'm allowed to say that X has to be greater than or equal to -4. But then what would I do for this bit? Can I say that it's gonna be less than or equal to 4? No, just less than 4. So I'm just gonna say just less than 4. Right, so they don't have to have both the same symbols when you're doing kind of like this like sandwich format of it's between two things. You could have one with a line and one without a line. That's totally fine, right? And then for Y, what's my lowest Y value? What's the lowest this function can be? I agree, Georgia, -4. And what about the highest? What's its highest point? -2. Right? So then when we go to say the range for this, right, YER, I have to look, because I'm like, okay, at my lowest point, I do have that open circle, but I also see I've got a closed circle at the exact same point. So this function can be equal to -4 for my domain. So I can use the less than or equal to -4 for Y, since it is defined there on Y, right? Even though it's an open circle there, at X equals -4, there is a Y value of -4. So I can include it. And then same thing, I can be -2. So I can use like the double equal symbol. Is that okay? So as long as that one is picked up for range, right? Another value is there that exists. I can include -4 in my range. It's just on the domain, I can't include it. Here, let's yes, -2. Okay, that I scooched over too far. There we go. Perfect. Okay. With this one, as you can see, I've got arrows. So that means like beyond this little snapshot of this function, it's just gonna continue going on and on and on and on. So then what would my domain and range be for this? Do I have any restrictions? So if I don't have any restrictions, I don't need to state anything. So I just say XER. Done. It's a real number. It's gonna be everything from -infinity to infinity. What about my range? Do I got any restrictions on my Y or what Y can be? No, so just YER. It'll go on and on and on and on forever. And you can even highlight like the fact that it's got arrows. It's gonna continue just going on forever. Okay, what about this W looking guy? I have to see, okay, I've got my arrows pointing here, right? So if you think about this, this is gonna just keep extending on and on and on, past on and on. So will I have any restrictions as to what X can be? No, right? It's just gonna keep extending. So domain is XER. Oop. Fancy bracket. But if I look at my Y's, I can clearly see, is this function ever gonna touch the negatives? Ever? No, right? Its cap is at 0 and then everything above it. So how could I write that in set notation? Thank you, Miss Georgia. Y has to be greater than or equal to 0. I can say it's equal because it's touching the x-axis, right? So it can be equal to 0, and then it just has to be everything above it. Right, so I'd say look for those clues. Look for the open or closed circles. Look for if your function has arrows, because that just means it's continuing or there's no restrictions. And then for something like this, we didn't have an open or closed circle, but we saw like there was a cap. Like it was not going to go any lower than 0. How is this? Is this okay? Coolio. Okay, you ready for your parent functions? Oh, it's okay. So you'll see it's a chart. So you've got your first two that you're already familiar with that you've done in grade 9 and grade 10. You've got the linear and the quadratic. So I'll refresh your memory on like what those parent functions look like. Your equation, instead of saying y equals, we're going to just say f of x equals just x, right? And if I made a table of values for this, I would see that, okay, if I'm going from, for example, -3 to 3. So -3, -2, -1, 0, 1, 2, 3. You'll see whatever I'm inputting is going to just be directly my output, right? If I plug in -3 into this function, it's just going to give me -3. If I plug in 0, it's going to give me 0. If I plug in 2, it's going to give me 2. So my inputs just match my outputs. 0, 1, 1, 2, 2, 3, 3. And when you go to plot those points, you'll notice, oh, this is just a plain line. It's like 0, 0, 1, 1, 2, 2, 3, 3, and I can do the same thing in the opposite direction. You'll notice this is just a line with slope 1. So if you think of slope, it's like your rise and your run. It's like you went up 1, over 1, if you need to draw that. And then this is more than enough for you to connect your points and draw. Voila. There's your line. Right? How would we describe the domain and range for this? Is there any cap on what the line can be? I've got arrows there. No, so it's just going to be, I'll say D is XER, and my range is YER. No restrictions. It's going to just extend into infinity and beyond. All right. Cool. Quadratic, that's the x squared. So again, instead of saying y, I'm just going to say f of x equals x squared. And if I do the same thing where I go from -3 to 3, just to see what this function is going to look like with my table of values. -3, -2, -1, 0, 1, 2, 3. The idea is that I'm inputting, or I'm taking my input values, I'm plugging them into this function, so I'm basically squaring whatever my input is. So if I square, if I square -3, I'm going to get +9. Thank you, sir. I think I left one for you back there. Same thing, if I square -2, I'm going to end up with +4. I'm going to just keep repeating. If I square -1, I'm going to get +1 versus 0 squared is just 0. And then you'll notice, because that parabola is that very symmetrical shape, it mirrors all of those y values are just going to repeat again. Because if I square 1, I'm also going to get 1. If I square 2, I'm going to get 4. And if I square 3, I'm getting 9. So you'll see that kind of like it mirrors again. And when you go to plot those mirrored looking points, you'll see, okay, at -3, I'm at 9. At -2, I'm at 4. 1, 1, 0, 0, and then I can just reflect into this axis. And it makes that U-looking shape. Which, try your best. It's okay if your lines are wonky. Okay, that's my quadratic. Now I have to think about domain and range. For domain, do I got any restrictions on this? No, right? Those arrows are indicating that it's gonna eventually just keep extending out and out and out into infinity. So XER. All parabolas have a domain of XER, right? My range though, it looks like I might be restricted. How would I say this? How would I say this range? Yeah, Adam?
YER is greater than, sorry, 0 is greater than y.
Yeah, vice versa. So y is greater than or equal to 0, or 0 is less than or equal to y. I guess you could say the same thing, but yeah. So y has to just be greater than 0. It's only positive numbers in this case, 0 and up. Solid. Those are your two friends that you know. Now for your new friends, we've got something called the absolute value function, which its equation looks like this. F of x is equal to, and then you'll notice these brackets that are just straight lines. They're on a computer. They're not on a calculator for some reason. At least I haven't come across them on a calculator yet. But this just means all values that go into the absolute value function come out positive. So if you input a negative value, instantly just turn it positive. So when you go to make like a table of values, for example, you'll see that, okay, if we got x and y, if I do the same thing, -3 to 3, -2, -1, 0, 1, 2, 3, anytime you put a negative value in here, you should just automatically change it to positive. So for example, if I'm inputting -3, psych, it's actually +3. Same thing, if I input -2, no it's not, it's +2. And I just keep going, 1, 0, and then if it's a positive number, I'm just keeping it positive. 2, 3. Well, and when you do that, by making these values positive, you're gonna notice that it kind of is almost like a parabola, but it's more straight. You end up producing this V-shaped looking graph, right, where it's straight edges. And that's how I always remember it, absolute value, so V for value. It also kind of looks like two lines basically coming together, one of slope -1 and one of slope +1, and together they make that V shape. Right? So with this one, like for example on a test, it's kind of harder because you can't use your calculator. There's no absolute value button, but you would just solve normally algebraically, like for example, and you don't have to write this down because we're going to do this in the transformations lesson, but just to get an idea of like how you would work with something like this, if I gave you something that was like 2x plus 1, ooh, not square, there we go, 2x plus 1, and then I told you x was like, I don't even know, -1. If you did like 2 times -1 plus 1, that's going to leave you with -1 in there, right? But because it's a negative value, I would just say, now this just becomes +1. That's my output value. That would be your coordinate point. So anything that's negative in there, turn it positive. Is that okay so far? Okay, what about domain and range? How would I describe that? Domain, do I have any restrictions? No, it's gonna keep extending on and on forever, so XER. Range though, do I have restrictions? Yeah. Hello, what's my restriction? 0. I have to be what, greater than or less than? Greater than. Hello, I left one there for you. Right, same thing as the parabola. I have to be greater than or equal to 0. I can touch 0 and I have to be everything above it. The square root function, which I think you also saw in some of your homework, because some people were like, what the hell is that? What does that look like? How am I supposed to know how to graph that? It's just the idea of like whatever your input value is, you have to square root it. So when you go to make a table of values, you're kind of confined to certain values. For example, can I square root a negative number? No, at least not in grade 11. That's above my pay grade. In grade 12, you might get to that. But in grade 11, we say, no, we cannot square root negative values. So I can't do -3 to 3 because there's not going to be any values at -3, -2, or -1. Your calculator will just say error, right? So I know at least I have to start at 0 because square root of 0 is just 0. And then you could go up 1, 2, 3, 4, but not all of those numbers are square rootable, right? Like square root of 2 is going to give you like an ugly looking decimal. So I'm just going to choose to go up by square rootable numbers. So like, okay, the next square rootable number is 1. Then the next square rootable after 1, 4. Yeah, 9. What's 1 after 9? What is it? 16, exactly. And I'm like, okay, that's enough points. Right? At least those numbers, those will give you like pretty whole number coordinate points rather than trying to plot decimals. And again, the idea of like function notation is I'm taking my input, I'm plugging it into the function, I'm going to see what I get out. So if I square root 0, I'm just going to get 0. If I square root 1, I'm just going to get 1. If I square root 4, what do I get? 2. What happens if I square root 9? 3. And square root 16? 4. Look at that. We're quick with it, and you'll see those are now your coordinate points. So now we're going to plot those. So we've got my first point at 0, 0. You've got your next coordinate point at 1, 1. Then you've got 4, 2, 9, 3. And I don't even think we have room for 16, 4. But you would see it would go somewhere like over here, where it looks like almost kind of like this rocket ship. That's how I always think about it, is like it's like launching and then just heading towards infinity, right? So that is the square root function, and it's confined to just that quadrant, right? Where you're putting in positive values, you're getting positive values out. So how would our domain and range look now? Because domain, we're definitely restricted, but what am I restricted to? Exactly, right? It's got to be 0 and then everything above it. I can't dip into the negatives. It's not going to go that way. Yeah?
Well, wouldn't it, if you ignore if you take away the real numbers one,
Mm-hmm.
because square root of a negative number would be like 4i, 4 imaginary,
Mm-hmm.
whatever, wouldn't that, how would you do that? Would it just be,
If you're including imaginary numbers, then we would be saying like x is an element of I, like for imaginary. But we are not doing that in grade 11. We're sticking to real concrete numbers that we can see. Imaginary numbers are like you can't see them on the graph, right? So, okay, we're stuck to that. And then what about range? What am I confined to in this case? Y has to also be greater than or equal to 0. Since I'm only going to increase positively, I'm never going to dip into the negatives again. It's not going to go that way. Right? Not so bad, right? 2 out of 3. This is okay. Okay, this one's the ugliest one. It's the ugly stepsister of the functions. Nobody likes this one. And it's called the reciprocal function. And when you heard the word reciprocal in grade 10, you heard negative reciprocal slopes, right? Those were perpendicular lines. Where, what did you do for perpendicular lines? What does it mean to be negative reciprocal? You change the sign and you do what? Flip. So this is exactly, the reciprocal function is you're taking x and you're flipping it. So it becomes 1 over x. So it's a fraction function. Yay. It's okay, don't worry. One of the key characteristics about this, though, is that what would happen if I put 0 into this function? What would happen? What would you get? 1 divided by 0? What is that? Not quite. Can you divide by 0? No. If you did 1 over 0 in your calculator, you would get error, right? Because you cannot divide by 0. We don't know what that is yet in the math world, so it's undefined. So there is something called an asymptote there, which I'm going to define on the next page for you. But when you go to make your table of values, you just can't include 0, right? So for example, if I go to do this and I say -3, -2, -1, I'll write 0 here, but we're going to see that there's no value for it. 1, 2, 3. If I'm inputting these values into my fraction, this is like me saying, okay, if x is equal to -3, then y is going to be 1 over -3. So -1/3. If I plug in -2, it's like I'm saying 1 over -2. And then 1 divided by -1, just -1. And then when you get to 0, this is where your calculator would be like non-applicable. No value for 0. Nothing exists there. And then you would see, okay, now it's going positive, where, okay, if I plug in 1, 1 divided by 1 is just 1. And then you're going to see the values kind of mirror again, where now it's just the positive version. So if I plug in 2, it's going to be 1 over 2. If I plug in 3, it's going to be 1 over 3, and so on and so forth. So you're getting these tinier, tinier, tinier fractions as time goes on. When you go to graph these, you'll see, okay, if I start in my negatives, at -3, I'm at -1/3, which let's call it about there, right? Try and be as exact as you can. At -2, I'm at -1/2. And then at -1, I'm at -1. And you'll notice as you, if you want to, plug in values that get closer and closer to 0. So when you start going into like x equals -1/2, x equals -1/3, or like even like -0.1, -0.001, the closer you get to 0, it's going to get closer and closer to this y-axis, but it's never going to touch it. And same thing this way. The higher your values get in the negative side, going towards negative infinity, the closer and closer you're going to get to 0, but you're never going to actually touch 0. So that's why it's like it's riding alongside those axes. And the same thing is happening up in that top quadrant. If we do the same thing of like, okay, I plot 1, 1, I'm plotting at 2, 1/2, and at 3, 1/3, you're seeing it's kind of making that curve shape again, where the more points I plot, I'm going to get really close to y equals 0, and I'm also going to get really close to x equals 0, but I'm never actually going to have y or x ever equal to 0. It's just going to get really, really close. Right? So we draw them super close like that, and then to draw the asymptote, which is the fun word that you're going to do on the next page, we usually dictate them or draw them to visualize them with these like dotted or like dashed lines going through the axes, being like this is kind of like a restriction. It cannot touch this boundary, right, to show off the restriction. Right. Is that okay? I know it's ugly. It's bad. It'll grow on you. It'll grow on you. So with domain and range for this, I see, okay, I do have a restriction here, but it doesn't look like I can say like x has to be greater than this or x has to be less than this, because I'm kind of breaking up my function into two functions, like two different things are happening in two different quadrants. So in this case with your reciprocal functions, all you have to state is just what x and y can't be. So in this case we're saying x is an element of the reals such that x just can't be 0. It can be 0.001, it can be -0.01, it just can't be 0. It can be everything in between it, just not that. And same thing with range. Y is an element of the reals, but it just can't be 0. It can be everything else but. So with these ones, the restrictions are a little easier because you don't have to find endpoints or describe it in terms of who's greater than what or who's less than what. You're saying it just can't be this, flat out. How's that so far? How do you like these 3 new functions? They're okay? Who's your favorite so far? Like, which one's the prettiest looking one? Really? Square root? I also agree. Square root, I don't know. It's just like it's satisfying. It's all positive all the way around. Okay. Ooh. And that's my blank. So those reciprocal functions, they've got that feature that's called the asymptote. Just a funny word, but it's just those invisible lines because you don't see them like if, for example, if you plug them into Desmos. Desmos doesn't do those like little dashed lines. So these invisible lines are like boundary lines that indicate where a function cannot exist or does not exist. Right, there's just no values there. And we said our function can get really, really close to those asymptote values, but they'll never touch it. Only in grade 12 advanced functions will you ever explore the rare cases where you can cross an asymptote. It's rare. You won't see it that often, but it sometimes happens. But in grade 11, we say you'll never cross it ever. And so vertical asymptote, that is just when you have division by 0. So if you've got 0 in your denominator at all, that just means that your function is undefined there. It doesn't exist, right? It's undefined. That's what your calculator will say. Therefore, we say that expression of the denominator can't be 0. So when we start graphing things that look like quadratics over quadratics, right? Stacked functions. You're just gonna say, oh, I've got a vertical asymptote there wherever or for whatever value that would make my denominator equal to 0. We can't have that. So for example, with these ones, if you've got 1 over x minus 3, I'm saying that this denominator cannot equal 0, where you could set this and say x minus 3 can't equal 0, and then I'm just isolating x, just like I normally would. So I'm gonna kick over that -3. I'm gonna say x cannot equal 3. Which is true, x can't be 3, because if I plugged in 3, I would get 1 over 3 minus 3, and 3 minus 3 is 0, undefined, right? And what that -3 means, just means that we're gonna draw our dashed line, which I'm actually gonna scooch this over a little bit, at 3 instead of at 0. So here's our function. Let's say at +3, it's about roughly like here. This is where our asymptote would be. And y can't be 0. We didn't change y at all. So now our function would look something like this. The same kind of like curve where you're not touching these asymptotes. You're gonna get really, really close to the asymptote. But now it's just like shifted over to the right. That's it. That was a little ugly. Right? What about the second one? What value of x would make that denominator equal to 0? 2 times something plus 1 would be 0. So even like try and treat it algebraically of like, okay, 2x plus 1 can't be 0. If I'm thinking about isolating x, what's like the first thing I can move in that expression? The 1, I agree. So 2x can't be equal to -1. And then if I want x by itself, I gotta divide by 2. So x cannot be -1/2, which that checks out, because 2 times -1/2, that makes -1, and -1 plus 1, 0. So it's undefined there. So again, that just means that's where your vertical asymptote's gonna be. So again, if you did like a quick little sketch, you would see at about -1/2, which I'm gonna roughly sketch, let's call that -1/2. -1/2, that is where now your function would exist or not exist. So it'd be slightly over on this side. And you'll see when we go into these functions in a little more detail, this is a transformation, right? My graph has shifted like left and right in this case. My asymptote has moved. So your denominator is telling you like where you're moving to or what can't your function be. For the horizontal asymptote, so that horizontal line, we are just saying that y cannot be 0. That's our line. We're not shifting it up and down yet for these regular parent functions. We're gonna see that when you move your function up and down, that will move the line, but that's coming. And in grade 12, you'll see sometimes, not only does it look like this, sometimes it looks like this, and it's slanted. So that's what's coming. But that is your introduction to the parent functions. So again, you've got your checklist here where I would be comfortable with at least knowing the parent functions, knowing these things that are called anchor points, which means like they're your solid, like original points on the graph, describing domain and range, and being able to kind of like talk about the characteristics about these parent functions. And you've got some practice questions, so you can use the time to work on those. If you want to ask me questions about 1.1 to 1.2, I'm there.